So basically, I'll explain about my problems, and then I'll talk about the oil equations and the related scaling problems, and then show some numerical experiments. Okay. So what happened is, there happens something like the circuit is broken, so short circuit happens, then there could be some accidents, so very big accidents, and that's why we need to study some high voltage, how to break the circuit. So, okay, so this is examples which we did experiment here. So this is around 500 kilovolt, and there appears arc. So you cannot easily break the circuit. So the insulation property of air is around 10 to the 5 volt per meters. So you need to disconnect this circuit. Okay. So this is the introductory model of the gas circuit break. So we have a very high voltage, like the million volt, and it's not easy to break the circuit. So what we did is the most powerful device is gas circuit breakers. So here is a electric rod. So this is some actuator, and this is electric contact, and actually the current is flowing from here to here. Okay, so inside this chamber there is some insulating gas. We call it SF6 gas. So SF6 gas is sitting here. So if there happens some short circuit, so we try to break this circuit. So this actuator will move the electric contact. Okay, so this is the real picture of a circuit breaker. Okay, so this part is the computation part, which we like to simulate on here. So this is a more detailed view of the real picture of a gas circuit break. Okay, so this is inside here. So electric load is here, and the current is flowing from here to here. Okay, so there is a gas, SF6 gas is surrounded on this chamber, gas chamber. Okay, so I'm sorry, it is written in Korea. So this is electric contact. Gas is here. The piston is moving here. Gas is pushing out from here, and since this is moved to the left, so the gas is filling in here. Okay, but the speed of gas is quite fast, so we need to analyze in these things. Okay, so this is the experimental pictures. Okay, a very short time. So this is 8.3 milliseconds, and this is the current profiles. And with these current profiles, there appears electric arc. So this is a very bad situation because of it means it failed to break the circuit. So the question is how effectively to cancel out this arc. Okay. So this device is called Papa type circuit break. So this is a gas is in here, and this piston is moving gas, and this movement, this electric rod moves left hand side very quickly, like 7 meters per second. So the gas is coming here. The gas is called the insulating gas. Okay, so the gas is supposed to disconnect on here. The current, yeah. Okay, so this is the more detailed picture of the arc. So what happens is this part is basically quite homogeneous arc. So electrons are moving very fast. But if you look at the boundary of this arc, there appears some turbulent motions. So what happens is to study actually more details, we needed to study the structure of this electric arc detail. But in this talk, we are just only give some fluid motions. So this is here. So as before, this is electric contact is moving left-hand side, gas is coming from here to here, okay? So the insulated gas is filling on here. So let me go to the more physics, okay? So these energy terms are ohmic heat because of the electron is flowing. It collides with some air particles, and there appears some ohmic heatings because this colliding means there appears some resistance. So there appears some ohmic heatings, and this is also because of during this collision, well, because of some quantum effect. So the electrons on the cells is escaping, and so you see about a very strong light is appear. Okay, so this is light is appear. So we have a natural radiation phenomena on the inside this gas chamber, and we have also, because of the piston is pushing out this fluid, there appears some fluid motions. Okay, and also, as I said, if arc appears, so because of the temperature go to the like 40,000 degrees, so the temperature is very high. So anything with this arc is melting down. So there appears some very strong or metal vaporization appears. So we need so that will deteriorate some insulating properties because of metal is vaporized. So we need to understand. So what we do is, question is, what kind of a model do you need to simulate in here? So the first quite good candidate is, because the current is flowing, we need might introduce some magnetic hydrodynamics, and maybe because of this some kind of avalanche effect, where we may have to consider about quantum mechanics, because of this is surface physics is coming in here. Also, so what we have to do is consider all these things, and the motion of fluid. So what kind of equation is necessary? Well, you may go to the very low level mechanics, like as Professor Tapping, you said, Boltzmann equations, or some other Euler equations, or Navier-Stokes equations. So for developing some numerical code or simulation program, we need to choose some right equations. But it turns out in these models, because of the speed of the flow is quite fast, so we may ignore some viscous terms. So just because the Reynolds number is quite high, so we ignore viscous terms. So the natural candidate is compressible Euler equations. So with some energy source. And furthermore, this is electric contact, and piston is moving. So the computational geometry has moving boundaries. So it's quite difficult situations to simulate here. Okay. So what the first candidate is, let's put some magnetic field here. So the equation is compressible Euler equations with some magnetic field because of the current is flowing. So this equation has basically around eight unknown variables, and we need to compute 8 unknown variables. Okay. So let me say it. So B is magnetic field, rho is the dense gas, and the V is velocity. And so we have seen already this equation before, right? So this is energy. So this is B square is the energy source coming from the magnetic field. Okay. So we just consider the computation of 1D magnetic, one-dimensional magnetic hydrodynamics. So even in case of 1D dimensions, so this our simulation shows there appears around 5 characteristics. So as he said, so there appears even for pressure control. So there appears rarefactions, and we have some shock phenomena here, and certainly there is some contact path. So this is the simulations of the pressure. So this is the direction of the similar part of characteristics. Okay, this is the density core. So here is you can see about the contact discontinuity. This discontinuity didn't appear before, but this density shows some contact discontinuity on here. So this is velocity profiles, and this is the direction of the y directions. So this is a magnetic field. So this says well, the computation of this introduction of the magnetic field is very difficult. So this 1D simulation shows to complete my real problem. So at this stage, we decided, well, let's consider magnetic field later. So instead of considering magnetic field, we just took only Poisson models to simulate this phenomena, okay? So this is the continuity equations. So you have seen already the Euler part. Remember, there is no viscous. So this is the energy equations and momentum equations and the continuity equations. Okay. So, but the very beginning, the same of gas chamber is actually symmetric. Okay. So, because of the symmetry, if you formulate it, there appears some source terms. It comes from the curvature terms. Okay, there is a source terms, curvature terms, and this source term has a curvature terms and ohmic heat and radiation and gas avulations and so on. Okay, so but I think because of the problem is too complicated at this stage, so we just stop considering the avulation. We will consider avulation a little bit avulation later, and we going to discard about radiations. So we just consider ohmic heatings and this is a curvature part here. Okay. So to develop the computational code, we took the idea of mesh-free schemes. Okay, so why we took mesh-free? So there is a very different method for the computations. So the usual scheme is just some finite difference, like the Goldorf schemes. So you solve locally Riemann problems, and the Goldorf scheme has locally Riemann solvers. So you give solutions. But under these moving geometries, okay, so although this is fixed geometries, when the geometry is fixed, maybe Goldorf scheme or some other finite difference scheme, there are many finite differences. They might be useful to consider, okay? But our real problem is the geometry is moving. That's the difficult part. So for the moving geometries, the idea is well, you just forget about the mesh. You just consider about some node, generate the node, and let the node move here. Okay. So we took the mesh-free schemes. Okay. Mesh-free scheme means we do not make mesh. We just consider some element basis. So let the basis, this basis function follows here. So in case of 1D shock tube, we did some experiment. Okay. So 1D shock problem. So there are no magnetic field. So our computation shows it's quite accurate. So we become confident. Okay, so let's use mesh-free schemes for this moving geometry here. Okay, so here is one more the benchmark problems. So there is some corner is here. So once the wave is coming here, shock wave is coming here. So it moves on here. So there appears some vortex appeared here. So this is the experiment. This is a picture by they took pictures, and our computation shows it agrees, almost agrees with this quadratic problem. So we become now very confident. Okay, so let's took mesh-free schemes to compute this gas circuit breakers. So that is the initial our confidence here. And furthermore, in case of mesh-free schemes, there are very nice idea called point collocations. So we don't need to actually consider differentiation by the weak formulations. So we can apply directly to the equations mesh-free. So that point collocation idea is developed by the Professor Do and Kim at the Hanyang Universities. His idea makes us to take this mesh-free scheme to compute these things here. Okay, so now we let the boundary moves here. Okay, so this is the boundary movings. So we appear some interaction between shocks, and with this is but look at the geometry. Geometry is rectangular. The geometry is a very nice rectangular geometry, so easy to compute. And we made some algorithms and shows all this the density and the pressure and the Mach number behaves very well here. Okay, but in these models, so far we didn't consider any only heat. We just consider cold gas. We call it cold gas because there is a low energy source. Okay, and furthermore, this flow is a rectangular flow. No actually symmetry is here. Okay, this is we did already 2 years ago. We did these simulations. Okay, and well, we check out our algorithm is good for the moving boundaries, and we did some known equations. We did compute, and our algorithm works at least for this 1D heat flow. And then we took the moving boundary here. Okay, but this is axis symmetry. So this right of the side is axis symmetry, and this is a rectangular geometry here. So you can see the difference here. Okay, the actually symmetric case shows a more stronger shock here. The concentration is stronger, but this is a rectangular case. Is the concentration along the axis is much weaker than this is a rectangular. This is an axis symmetric case. So this shows much stronger phenomena concentration of the axis here. Okay, and the propagation of this discontinuity is even faster than the rectangular case. Our simulations shows. Okay. So this is we consider real geometries. So this is a real geometry, and this is a gas chamber, and the piston is coming from left hand side, and this electric counting is moving. So this is a real geometry. So we took these real geometries, and so with this real geometry, so far we didn't consider any electric field here. This is only just the flow of the gas. So we did an experiment, numerical experiment, and there appeared about some leakage of the gas on here, and it goes here. So, and we also compared with the real experiment. So we put the pressure gauge on top of here, or on top of here, pistons. On the piston, we put the pressure gauge, and we compared our simulation results and the measurement of the pressures. So it turns out, well, it's very accurate. So we become very confident about these models. And this is a movement of the density and the Mach number, and also all the other velocities here. Okay. This is more experiment, and this is a piston is moving here, and the shock is reflected and it's interact with each other, and our simulation shows. Okay. So now, but this electric current is flowing from here, and when there appears a very strong current is coming here, and it's not easy to break here. So what we have to do is, there might appear just some electric arc here. So what I mean is, so there is some, like this plays like the arc nozzles. So there appears some strong electric arc. So you have to consider now the electric arc. So that part is a difficult part. So this is now only heating. So let me explain about our models. Okay. So this is arc regions. So you can assume electric load is content is here. So arc is generated here. Okay. So this part is the electron is flying here. For example, left to the right or right to the left here. So outside this region, let me assume there is no electrons here. So in this region is the electron is flying. So the speed of electron is 8 kilometers per second, and this is the speed of electron. Okay, and the speed of ion is about 4 meters per second here. Because it's related to the mass ratio. Mass ratios. So the mass ratio between electron and the ions are basically 1 to the 2,000. Okay, so ion is around 2,000 times heavier than electrons. So therefore, the speed of electron is too fast. So it's not a good idea to put all things together in too much physics. So what we have to do is, what we are interested in is only the temperature and the density of this region. So what the idea is, I need some eraser here. Yeah. Okay. So what our idea is, so if this is arc region, so we assume left on the side is the constant voltage here. So this is left on the side is, for instance, V0, and the right on the side is equal to the V1. So there is a potential differences. So then we need to know what kind of energy source is coming here on this region here. So what we do is, once V0 is here, and assume this is along this left on the side, let us assume it is a Neumann data. So for example, dV, dE equal to 0. So there is the voltage has the potential has so Neumann properties here. So now here inside here you have certainly the Poisson equations. So divergence of rho of gradient of, for example, P, let us assume it equal to V here, equal to some 0 here, because of there is no thing here. So the potential, the voltage potential has this kind of equation. But this rho is conductivity here. I may have to put a different thing here. Okay, but this conductivity is, depends on the density and the pressure and certainly temperature here. So we have the gas, and this conductivity coefficient has been already calculated from the experiment. So we don't need to worry about too much. And what I did here is, okay. So the question is, how can you find the voltage on B0 and B1 here? So the idea is we compute the power here. Okay, the power is the sigma E square is this is energy here. Okay, this is the energy of at each point. So if you integrate along this all volume, so now you have the effective power here. So the change of the energy each time here. So we have but this power is usually the arc voltage times arc current here. So that's the formulations here. So once we measure the current here, from left to the right, so if you measure current, then we can compute voltage differences. So now we have a voltage differences here. So left hand side and the right hand side, once we have voltage differences, we have the conductivity coefficient is been already done by experiment. So we solve these Poisson equations here. So once we solve these Poisson equations, we can compute the current flux and the electric field. So this is E coming to this E and sigma E squared is the energy source. This is only heating. So this will heat our gas here. So this will come in here, our energy equations. So let's go back. I have to go to oil equations. Yeah, okay. So it will come on this energy equation here, electric field here. So it's coming on here, and you see the Poisson equation sitting here. So it's a combination of a Poisson equation and the fluid equations. So we have some closed systems, and if you compute, and our we actually did the computation, but I didn't bring the picture in here. Okay, so we did compute, but basically the pictures are quite similar to this is the axisymmetric case here. Okay, so how much time is left?
10 minutes.
10 minutes. Okay. So I think I have shown most of our simulations, and yeah, this is I think it's missing. Our pictures are missing here. So this is the geometry. This is the mesh which we made on this electric arc. So this is each node. As I said, there is some basis functions at each node, and we solve the Poisson equations. And this is a distribution, the density of electric field here. Okay, so that's the computation of our the Poisson equations, and the fluid field has been already computed by the previous pictures. So now I have some modeling questions. So what is the right model to consider further? So the important thing here is, so this is some melting down of the metals. So to consider this is a melting down of these things, we need more physical models. So we call it surface physics. So I'm not going to go this surface physics. We have to consider some Johnson effect along the surface physics. But to consider this Johnson effect, we have to go to more low level, like quantum mechanics plus or either Boltzmann type equations to consider some melting down here. But that part of the physics is still a little bit away. Hope next year I could include evolution and the melting down of metals, and include to discord, and so and the discord is going to be used to develop some other company, I think, in Korea. So we have some Hyundai and the Samsung and the Hyosung. They are developing gas circuit breakers. So we are going to give this idea, this device, this numerical device, to develop a better gas circuit breaker. So I think this is more or less the end of my talk. Thank you very much.